Okay, why don't we start? I don't think my mic is working, so I'm just going to take it off. So just a couple of logistical questions. We're almost at the end of the semester. The assignment 1 and assignment 2 and assignment 3 are going to be graded hopefully by the end of the week, so we'll get the feedback. You should be focusing on your projects, because projects are due on December 4th, which is a week from today. So make sure that you talk to TAs and then submit your projects on time. I don't think I'll be able to give any extension. As I mentioned before, we have over 100 projects to grade. And we only have 2 weeks to grade the projects, because we have to submit the grades to the School of Computer Science by December 15th or 17th or something like that, basically. So there is no way I can give you extension. I know a few people asked for the extension, but I think that there's just no way around it, and hopefully you've been working on your project over the course of over the time of this course. So hopefully it shouldn't be a problem. So you should really be focusing on your projects. Next Monday is going to be our last class. So we're going to have a class next Monday, but we're not going to have a class the following Wednesday. So we're going to have class this coming Wednesday and Monday. So we have 2 lectures left. Today we're going to finish variational autoencoders. And then the remaining 2 classes, I'm going to show you some examples of using deep learning models for reading comprehension, and maybe a little bit on reinforcement learning, just to give you an intuition of what these different branches of research are. Okay? Okay, so today let's continue looking at variational autoencoders. Just a very quick refresher. We've started looking at variational autoencoders in our last lecture. So this is the motivation. This is what the variational encoder looks like. You have a generative process. Given some prior with a latent space, you're generating the input data. And then you also have, I just plug this in. And you also have a recognition or approximate inference part, which is another neural network. Here is an example of what the VAE is. It defines a generative process in terms of the sampling through the cascade of hidden stochastic layers. In many cases, instead of having multiple stochastic layers, you only have a single stochastic layer, which is just the top layer. So you have a generative process. Theta, throughout the rest of today's lecture, is going to be denoting the parameters of VAE. This is just a reminder. L is the number of stochastic layers. And you always make an assumption that sampling from conditional probabilities and evaluating these conditional probabilities is a tractable operation, right? So you can always compute these conditionals, P of HL given HL plus 1. Now, each term here can be, may denote a complicated nonlinear relationship, so it could be a neural network with deterministic layers on its own, okay? So for example, here's one instance of variational autoencoder. You're defining the probability distribution over the X. This term here, the conditional probability of H1 given H2, denotes a 1-layer neural network, right? So it could be a nonlinear relationship between H2 and H1, right? Because it goes through nonlinearity. So the recognition network is defined in terms of a similar factorization. Right? You basically say, given the X, infer the states of the hidden variables. And again, each conditional on its own can be its own nonlinear deep neural network. Both are valid. So now we're going to be making assumptions. We're going to make a few assumptions, common assumptions to make. We're going to assume that H capital L, the top layer, is given by a Gaussian distribution with zero mean covariance identity. It could be uniform distribution, could be simple Gaussian distribution. And there's been a lot of work trying to extend. You can stick, for example, an RBM model on the top layer, or different extensions are possible. But we want to make an assumption that the prior is a simple Gaussian, and the conditionals are also Gaussians with diagonal covariances. Okay. So this is the simplest assumption we can make. We can say these conditionals in the recognition models are both going to be Gaussians. Now, one thing to note here is that even though the probability of HL, given HL plus 1, could be a Gaussian, the mean of the Gaussian could denote a very nonlinear relationship between HL plus 1 and HL. So the mean could be a nonlinear transformation of the layer above, stochastic layer above, right? So it can actually go through multiple deterministic layers. How do we do parameter learning? So as the name implies, we're going to be using variational inference, okay? So the VAEs, the variational autoencoders, are trained to maximize the variational low bound. And we've talked about variational low bound in this course. That's the definition. We can also think of it as trying to optimize the data log likelihood and the KL divergence between the true posterior, P of H given X, and the approximating posterior, Q of H given X, the other way around, right? So P of H given X would denote a true posterior in the VA, in the variational autoencoder, in the Helmholtz machines. Generally, that operation is intractable. You can't compute the true posterior because of nonlinear relationships. And if you have multiple stochastic layers, nonlinear stochastic layers, computing the true posterior over the latent space is an intractable operation, right? So we're always going to be approximating it with a deterministic or some form of a deterministic neural network, much like what we do in variational inference. Now, these variational approach have been around for quite some time. In fact, the original Helmholtz machine paper back in '95 introduced this variational bound. But the problem is that it's very hard to optimize this variational bound with respect to the recognition network Q, right? You can take this lower bound, differentiate with respect to parameters. It's easy to differentiate with respect to generative model, given your recognition model, but it's difficult to differentiate with respect to recognition model, given a generative model. So it creates a lot of, it's basically you get a very high variance estimate. And it's very difficult to optimize, right? So optimizing the variational bound sort of is non-trivial. And one of the key ideas of Kingma and Welling was to use so-called reparameterization trick, which allows you to get a much smaller variance whenever you're estimating the gradients of this bound. So there is one simple trick that allows you to optimize this variational bound fairly efficiently. And that's the reason why VAEs have become so popular, because actually optimization has become a much easier task to do. Okay? So let's look at the reparameterization trick and sort of understand the idea behind what we're optimizing here. So let's look at the following formulation. Let's assume that the recognition distribution is Gaussian. Okay, so we're going to say at the inference step, the probability at some layer HL given layer HL minus 1 is going to be given by a Gaussian distribution, the mean, as a function of HL minus 1. Remember, this function itself can be a nonlinear neural network, right? Or it could be some nonlinear function approximator. You can basically stick whatever you want to stick in it. It doesn't have to be a linear function of HL minus 1. And we're going to parameterize our variance as a function of HL minus 1, which again could be a nonlinear relationship, right? So you take HL minus 1, you pass it through multiple deterministic layers, and then you get the mean of a Gaussian distribution. Okay? Is that clear? And that creates nonlinearity between different stochastic layers. In traditional variational autoencoders, you only have a single stochastic layer, which is the top layer. Everything else is deterministic, right? So in this case, you would say the approximating distribution Q of the top layer of VAE, given the data, is going to be given by a Gaussian distribution with mean given by nonlinear transformation of the data, and the variance given by some nonlinear transformation of the data as well. Okay? Think of, traditional neural nets for regression, for example. It's exactly what the Qs would be here. Now, alternatively, you can express this in terms of auxiliary variables. So I can write this distribution as follows. I can say sample epsilon from Gaussian distribution with zero mean and variance identity, or covariance identity covariance. And then once I have this random variable, I can write down HL, the states of the hidden layer at layer L, as a function of epsilon and the function of HL minus 1 using this equation, right? So I can take my covariance, raise it to the power 1/2, multiplied by epsilon plus the mean. Okay? This equation is deterministic equation. There is no stochasticity here. Once I give you epsilon, right? Once I give you samples, in this case epsilon from normal 0, 1, now I know deterministically what my H layer, the states of my layer HL should be, right? Using this transformation, right? And there is nothing surprising here. This is standard way of sampling from a Gaussian. In fact, most of your algorithms, when you sample something, when you say sample me from a Gaussian with mean mu variance sigma, right? Standard algorithms basically sample from normal 0, 1, you know, multiplied by standard deviation at the mean, and then you get a sample from whatever Gaussian with a mean and corresponding variance, right? So this is just a simple transformation that you have. Okay? Are there any questions? This is the key for getting VAEs working, basically. And the idea is very simple. Something interesting happens. Notice that this epsilon here doesn't depend on the parameters of VAE, right? It's just a simple normal with 0 mean variance identity, right? So now somehow we are decoupling the stochastic part, which doesn't depend on the parameters, and deterministic part, which depends on the parameters, right? And there are some distributions where you can do it, and you know, if you can do that particular separation, then you can use VAE. So assume that Q is given by, again, normal, or this is our parameterization that we're going to be using. Okay? So why is this helping to us? There is no, you know, why isn't sampling from the Gaussian with mean mu and sigma versus sampling from 0 identity and then using this transformation is useful to us? Well, it turns out it's useful to us because the recognition distribution can be expressed in terms of a deterministic mapping. The entire recognition distribution can be expressed in terms of epsilon, x, and theta, right? With epsilons given by epsilon 1 up to epsilon L if you have L stochastic layers. If you have one stochastic layer, it's only going to be single, you know, single epsilon. If you have multiple stochastic layers, you can have multiple epsilons. But now, once given those epsilons, this entire recognition model is just a deterministic encodings, just a deterministic encoder, right? So this is a deterministic encoder. If I give you the epsilons and I give you x and I give you the parameters, I can infer the distribution over my latent space, right? It's just a feed-forward deterministic neural network. And this is distribution of epsilons here does not depend on the parameters theta. That's important. We'll see later why this is important to us, right? So we have some stochastic part which doesn't depend on the parameters, and we have a deterministic part which depends on the parameters, right? Now, let's look at why it's helping us. Let's look at the gradients of the variational bound with respect to parameters, okay? So the gradients with respect to both recognition and generative parameters, I can write down this way, right? It's the gradient of the variational bound. That's the definition of the variational bound. Or I can do the following. I can say, well, it's actually the gradient, and I'm going to do reparameterization. I'm going to say it's the expectation with respect to these epsilons that are coming from normal distribution with 0 mean covariance identity. And now I have log of the ratio P over Q, where everything here is a function of epsilon, right? And the data and the parameters, okay? Right? It's exactly this. This is equality. There is no, you know, uncertainties or approximations made so far. This is an equality, right? Now, something interesting I can do. I can take this derivative, which is derivative with respect to parameters, and because this expectation does not depend on the parameters, I can take the derivative and put it inside, right? So I can take this derivative and put it inside the expectation. And this is, again, an equality, right? Because my expectation doesn't depend on the parameters. So something interesting happens. In this mapping H here, is a deterministic neural network for fixed epsilon. Once I give you epsilons, this whole thing is deterministic. And this is also deterministic, right? So now something interesting happens. I take expectation with respect to these epsilons. These are my stochastic part of VAE, sample from normal zero identity, and then I take the gradients with respect to the log of the ratio. It turns out that this derivative, I can just compute the entire thing using backpropagation algorithm. So I can backprop through the generative part, I can backprop through recognition part. It's equivalent to using an autoencoder. That's why it's called variational autoencoder, because if you actually compute the gradients, here's an encoding part, here's the decoding part. If you actually compute the gradients, there's going to be a term corresponding to autoencoding. Given the x, infer the h's. Given the h's, reconstruct back the x. And then there is an entropy term. But this part here is essentially an autoencoder. This is the encoder, and P is the decoder. So that's why it's called variational autoencoder, because you're optimizing the variation bound. It's a proper generative model. Generally, autoencoders are not generative models. Autoencoders can only be used for encoding the data into the latent space and just using reconstruction. It's not a proper generative model. It doesn't define a proper probability distribution over the input space. It's more of a feature extraction technique or compression technique. Variational autoencoder defines the distribution over the input space. So it's a proper generative model. It's a proper probabilistic model. And you have in its gradient the computation of, an autoencoder, which gives you to compute the to optimize for the parameters. You're actually following the gradients of an autoencoder. This is also a very interesting observation, right? So why does it give us smaller estimates of the variance of the gradients? The reason why is, you think about this. What does this equation tell you? The first equation is basically tell you compute the expectation and then take the gradient. So it's equivalent to take the average and then compute the gradient, so move the average. This equation is telling you, no, take the gradients and then take the average, right? So you actually have a much better, much lower, you have basically low variance estimator here, right? Because you're taking expectation of the actual gradient. Instead of taking the overall mean and moving the mean, you're essentially taking the gradients and then averaging the gradients. So that gives you a far better estimate of the gradient. And not only that, it's now you can compute this gradient with respect to both recognition parameters and generative parameters. So it's one objective and you're optimizing the variational bound jointly. This is something that could not be done before, either because the variance of the gradients was too high or people use different objective functions. So this is a very nice and very clean and very simple trick to use, right? You can also think of it as somehow you're separating the stochastic part. You still have to estimate the gradients, so you still have to sample epsilons, but you're separating stochastic part, and then you have a deterministic part. So it's almost like backpropagating through latent variables, right? Remember, these h's are latent variables. These are stochastic latent variables, right? But by using reparameterization trick, you're actually backpropagating through the latent variables themselves, which is kind of neat if you think about it. So how do you compute the gradients? So let's compute the gradients. So this is the estimate of the gradient. This is a quality. How do we compute the expectation? Well, we're going to approximate expectation by generating k samples from epsilon. So you're drawing from normal 0, 1, essentially. And you just compute the gradients of the log of these importance weights. And these important weights are, in this case, these are normalized importance weights, are the ratio of the joint to the approximate conditional. Right? That just comes from variational bound. So we're just using Monte Carlo approximation here. Very simple. Right? In practice, actually, to save for computation, you're actually drawing only a single sample. Right? Draw one sample, and then compute the gradients, and then do parameter update. Draw one sample, do parameter update. So low variance, as it uses the log likelihood gradients with respect to the latent variables, right? So you are actually computing the gradients of the log of the ratio, and you're backpropagating through the parameters of VAE. So one of the things, right, so this is something that you can do. It's very easy to implement. You can compute the gradients. There is if you actually compute the gradients, again, it corresponds to essentially doing autoencoder, your normal autoencoder, and then there are gradients with respect to Q distribution, sort of, you kind of have to take that into account, but roughly it corresponds to doing an autoencoder. So the variational assumptions must be approximately satisfied. Remember, when we looked at the variational inference, remember we've looked at the case where if we use variational approximation, like a fully factorized variation approximation, which is what we're doing here, you can only capture a single mode in the posterior. Right? Remember those graphs where we looked at the KL between Q and P, and you have two modes in the data, the KL would only pick up one, or the variational inference would only pick up one mode. If you use KL the other way around, you kind of spread your mass around both modes. So the posterior distribution must be approximately factorial and predictable with a feed-forward neural network. Right? So that's one of the common assumptions in VAE. One thing you can do is you can relax these assumptions using tighter lower bound on the marginal likelihood. So there are actually ways of trying to basically relax these assumptions that your posterior has to be a single mode posterior. So let's look at how we can do that. There is a class of models called importance-weighted autoencoders. They are computationally a bit more expensive, but instead of relying on drawing a single sample from the posterior, what you can do is you can define this variational bound. So the bound here is given by, instead of drawing a single sample H from Q, what you're doing is you're drawing multiple samples, K samples from your approximate posterior, and then you're taking log of the average, right? So this is different from what we've seen before, where you're drawing multiple samples and then you're taking the average. This is actually taking expectation of the log of the average. So H1 through HK are sampled from the recognition network, right? So we're taking expectation over multiple samples from Q. Or you can also write it in this way, where again these WIs are normalized importance weights, right? These are ratios P over Q. So obviously this is more expensive, because even if you could compute these expectations, approximating L sub K would be K times more expensive, right, in general, because you have to draw K samples. You can show that this is a low bound on the marginal likelihood. So we're still looking at the lower bound. And the way you can prove it is you can basically say, well, the variational bound is expectation of the log of the average, which is always bounded by log of the expectation, right? What is the log of the expectation? This is just by definition log P of X. So you can compute that because it just basically comes down from this expression here. You can take the expectation, you push it inside. Expectation with respect to Q of the joint divided by Q. Q and Q cancel out. You take an expectation, you get back the original log P of X. So this shows you that this particular approximation here is actually the bound on the log, on the marginal log probability. This is sometimes also referred to as multiple sample bounds, right? So instead of drawing one sample, you're actually drawing K samples. In special case, when K equals 1, you're drawing only one expectation, taking one expectation. This is the same as standard VAE objective. So this is a standard variational objective. One interesting thing about using these multiple samples is that using more samples, you can improve the tightness of the bound. In fact, you can show that using more samples can only improve the tightness of the bound. So in expectation, your bound will improve as you're drawing more samples, right? Now, this result only shows an expectation. Variance is something that's a little bit more difficult to control, but in expectation, you basically have these inequalities, which is kind of nice, right? Because if you think about this, we've talked about variational inference, right? And we always said, well, what happens in variational inference? In variational inference, you have some approximation Q, and you're doing optimizing the variational bound. Once you've optimized the variational bound, there is always going to be a gap, right, between the true log likelihood and your variational approximation, right? So you will never get the truth. You will never get the correct posterior. There's always going to be a gap, unless your Q distribution is in the same family as your true posterior distribution, right? When you use true posterior distribution, you basically get the bound that's tight. So you have the correct posterior. This result is basically showing that by drawing more samples, you can make this bound as tight, you can make this bound tight, right? So you can decrease the gaps. It's kind of a neat combination of variational inference and Markov chain Monte Carlo based approximation, where you can say, if you want to spend more compute, you can show that the bound becomes tighter, and so your approximation to the posterior becomes better. Obviously, as k becomes an infinity, the bound is tight. But you can control, right? Based on computation, if you want to use more compute, you can prove that you get tighter bound. Or if you don't have a lot of compute, then you basically stick with the variational objective. So on one side, you have the proper approximation. On the other side, you have VAE, variational approximation, which is cheap. This is more expensive. So you can trade off computation for correctness, basically, which is very nice if you think about this. The more compute you do, the more correct you get. The less compute you do, the less correct you are. And so here, again, if this ratio is bounded, which is most of the time it is, obviously we'd like it to be bounded. Having this ratio be unbounded is kind of a funny thing to even think about. Unless Q is assigned some small probability into places where P is so large, then you can get unboundedness. But if this ratio is bounded, then as k goes to infinity, this bound, this multiple sample bound, actually approaches the true marginal likelihood, right? So that basically, again, is a class of multiple sample bounds that kind of combine VAE or combine variational learning with with Monte Carlo based sampling. This is important sampling effectively. And so you can get, again, trade-off accuracy versus compute. Okay? So we can use the unbiased estimate of the gradients using reparameterization trick. The same reparameterization trick applies here. You can basically sample a bunch of epsilons, right? Remember, each epsilon itself could have multiple layers if you have multiple stochastic layers. So you have multiple epsilons. This is just number of samples. And then you take the gradient of the log of the average. It turns out that you can actually write this down this way. Intuitively, what this is you essentially have importance weights. These are normalized importance weights, W hat here, and you're taking the gradient. Yeah. So what happens here is you look at the ratio of W with the normalized weights. So this is essentially telling you something interesting, where these weights are the ratio of the joint to the conditional. Essentially what this is saying is it's saying the following. If I sample from the posterior, if this posterior has a good reconstruction, assign it a larger weight. If this recognition has bad reconstruction, assign it a lower weight. Right? That's what this term is telling you. And this term is just basically telling you what's the probability of getting to that latent space. Right? So if I look at differences between the two bounds, this is what we have using Monte Carlo sampling. So you're drawing multiple samples and you're looking at the weights versus, if you're drawing multiple samples using VAE. Right? And VAE, you take the average. You always take the average. In whereas in using the Monte Carlo based estimate, you're taking the weighted average, right? That's the only difference when you're doing the estimation in both objectives, which is kind of nice, right? Because if you think about Monte Carlo estimates, you're drawing multiple samples, you're taking the average. That's what happens with variational objectives. If k equals to 1, you're drawing only one sample, both objectives are the same, right? Whereas I-way objective importance weighted autoencoders, you basically weight the gradients by the importance weights. And again, these important weights are essentially telling you, if I draw a sample from the posterior, from my recognition network, and then I reconstruct back the data, if my reconstructions look good, and this is a good sample. If my reconstructions look bad, this is a bad sample, right? So you're adjusting your importance when you're computing the gradients. Computationally, both are equivalent. One is just a little smarter way of doing it. And so let me show you the intuition. So what's the intuition behind VAEs and I-weights? If I look at the gradients of the importance weights, right, that appears in both equations, in VAE and I-weigh, you basically have the gradients of these two terms, right? P over Q. So what is this guy trying to do? You have a deterministic encoder given V and epsilons. You have a deterministic encoder, and then given the epsilons, you have a deterministic decoder. So the first part of the VAE objective is just deterministic encoder-decoder. The first term, the decoder, encourages the generative model to assign high probability to each conditional, right? So decoder is basically saying, make sure that whatever my encoder is saying, I can correctly reconstruct, this from this. That's effectively what autoencoder is trying to do, right? Autoencoder, remember what's an autoencoder. Given the input, you encode to the latent space, and then you decode. And you're always trying to, have the best reconstruction, which is essentially what this thing is trying to do. And the encoder encourages the recognition net to adjust its latent states so that the generative model makes better predictions. So it's trying to say, try to find the states of H1 and H2 such that the generative model can now reconstruct these states fairly accurately. So both of them are doing the same thing. That's exactly what the autoencoder would do as well, right? Try to figure out what these states should be such that the generative model can reconstruct these states accurately. So this is exactly what the first part of the objective looks like. Now, if you only have this first part, this would just be your standard autoencoder, right? If you only have the first part. The second part encourages the recognition network to have spread out distribution of predictions. That's exactly what it's trying to do. It's trying to inject uncertainty. And this is why this is sort of, this essentially comes from the entropy term. So it's trying to say, don't, given the data, actually try not to make a point estimate of the latent space. Try to make this be uncertain or spread the distribution out. So you have two competing terms, right? The autoencoder is obviously trying to say, given the input, find me precise latent state so I can have accurate reconstruction. The second term is basically saying, find me the posterior such that my distribution is as spread out as possible. So it's kind of corrupting or making your model not to make very precise, have a very precise posterior. Because ultimately you are building a generative model. So this comes up from the objective, which is kind of interesting, right? Because you effectively have an autoencoder, and you have the second term, which basically says, make sure that the posterior of the latent space is as spread out as possible, right? So you're fighting both of these terms. So here's a couple of examples. So let's say we've looked at the two architectures. You have a single stochastic layer. This is a typical variational autoencoder setup. Okay, you have 50-dimensional latent space, which is Gaussian. You pass it through deterministic layers, and then you get your output X. And then you have the second architecture. In the second architecture, again, you have two stochastic layers, and you have deterministic layers, right? So you have both stochastic and deterministic layers. So both of these networks, you can train them, right? This is your standard VAE. This is a little bit more advanced model where you have stochastic layers mixed together with deterministic layers, right? So it's a little bit more of an extension of VAE. So here's what happens if you use, the MNIST dataset to actually get negative log likelihood estimates. You can see that with this one stochastic layer, as you increase the number of samples, your standard VE doesn't really improve by much, but the importance weighted autoencoder actually improves. And that gap is fairly significant, statistically significant gap. So importance weighted autoencoder, when you're using multiple samples, your bound becomes tighter, and you actually get better results. If you get the second stochastic layer, you can see the gap is even bigger, right? So you go from 85 to 82. So this is a larger network with 2 stochastic layers. One interesting thing about VAEs in general is that if we look at the number of active units, it's not typically utilizing a full capacity. So for example, in standard VAE, the number of active units is only 19, 20, and 20, right, out of 50 dimensions. So it sort of has this property of not using its entire capacity. If you look at the 2 stochastic layers, then in standard VAE, the first layer effectively only using 17 units, the second layer only using 5 units out of 50. So it has this notion of somehow not really fully utilizing the capacity of the entire network. So both VAEs and IWAs tend to run latent representations with effective dimensions far below the capacity. Right? So that's an interesting result, or it's an interesting observation. So why? Why is this happening? And one suggestion is that maybe the optimization is not there yet. Right? In fact, when you're building multiple layers, you basically, it's very difficult to make sure that the network is actually using fully the capacity that you're giving it to. So this is essentially what happens is that this is just a representation looking at the covariance, which allows you to analyze which units are active, which units are not active. And for a lot of examples, these are the number of units that are effectively dying out or inactive. And these are the number of units that are active, that actually do the modeling part, which is kind of interesting. So there's been a few papers, research papers that basically try to fix this problem by introducing either additional constraints or additional priors in the latent space, but effectively your standard VAEs have this problem. One interesting thing to note is that, for example, let's say I train the model using VAE and I get negative log likelihood of 86 knots. So low is better. If I use IWA with 50 samples, I get 84 knots, or 85 knots. But then, if I actually take the first model that's trained using variational autoencoder and then apply importance-weighted autoencoder, you get the reduction in the numbers. So it basically is telling you that this model can improve upon VAE objective. But if I take IWA and then from that point start training using VAE, the negative log likelihood actually goes up. So it's basically saying you're messing things up, right? So it's almost like if I use IWA to train the model and get to some performance, if I start proceeding training using standard objective, VAE objective, then my results get worse basically, right? So that's what it's showing, and then generally these are the results on the OmniGlot data set. This is a slightly different data set from MNIST, which is these handwritten characters, and you basically see similar performance, right? You get sort of the reduction from standard VAE if you're actually using these multiple sample objective, and there's been a few papers extending this work, basically showing that if you're willing to spend more compute, you can get better results. Right, and this is what OmniGlot data looks like. Here's another thing. You can use 8x8 patches. There's been a lot of work where people try to build generative model of in this case, it's a BSDS data set. These are small 8x8 natural patches. And there's been a lot of work trying to report test log likelihoods on 10 to the 6 8x8 etches extracted from BSDS data set. And there is a proper evaluation protocol, right? So there is a proper evaluation protocol for actually computing the log probabilities on this data set. Again, these are small patches, but it's a very good way of doing proper evaluation of generative models. Okay? And so using that, you basically have a whole bunch of different models. These are a little bit outdated results, but nonetheless. One interesting thing to note is higher, in this case, higher is the better. So if you use PCA, you only get 96 knots per image. If you use IWAs, you get better results, and the best results we're using neural autoregressive density estimation model, which is essentially similar to as a precursor to pixel RNN or pixel CNN that we've seen in this class before. So these models are by far, even today, better generative models. When you're trying to predict one pixel given the previous pixels using some complicated nonlinear neural network. So it's basically showing that these models are pretty good at modeling densities, much better than variational autoencoders. And these are what the filters look like if you actually train them using VAE objective, which is pretty nice. These are kind of low-level filters that used for modeling image patches, small image patches. So it kind of have interesting structure that you're discovering. And again, this is all done completely unsupervised fashion, right? You're just trying to model the densities of the data. So let me show you one example, example of where these models can be applied. I've shown you these examples before, these are motivating examples. Can we generate images from natural language descriptions? Here's some examples. Stop sign is flying in blue skies, yellow school bus is flying in blue skies, herd of elephants is flying in blue skies, and so forth, right? So you can generate funny looking things. It's very difficult to generate realistic looking elephants, although maybe with GANs you can probably plug something in to get something better. But here's what the model looks like. It's basically a series of variational autoencoders chained together. You can think of them as stochastic recurrent networks or a chain sequence of VAEs. And the idea is simple. You have some encoding of a sentence using bidirectional LSTM, bidirectional RNN, something we've talked about in this class. And then based on that, you have a generative RNN that generates a sequence of patches that places these patches on the canvas and then generates the image. The important thing is that at each time step, you effectively have a variational autoencoder. So you have an inference network and you have a generative network, right? It's just extended through time. But each individual slice is exactly the variational autoencoder. So how do you incorporate, you can also think of this whole framework as a sequence-to-sequence framework. Caption Y is represented as a sequence of words. Image X is represented as a sequence of patches drawn on the canvas. And then you have attention mechanism. You can have attention over words, and you can have attention over image locations. So depending which word you're paying attention to, you can choose which image location you want to paint, right? So you're trying to combine attention over which words as well as where you should be painting. And representation of the whole sentence is given by bidirectional LSTM. So this is something that you guys have seen before. You encode the whole sentence using forward RNN and backward RNN. These are LSTMs, and then you're concatenating them together. This is the draw model of Gregor et al., where you have a write operation. I don't want to get into too many details, but essentially at each step, your model generates a P by P patch. Then it gets transformed into W by H canvas. So this is canvas. So this is specific patch that you're trying to draw. And then you have specific transformations that look at filter location and scales and so forth. And then you have a writing operation, which essentially applies these filters to generate a particular patch. Right? If you're interested in this model, you can look at the paper that describes precisely what these operations are. So now you have a generative network, which you can think of it as a stochastic recurrent network or a chain sequence of variational autoencoders. Right? It's an extension of VAE when you're taking time into account with a single stochastic layer here. You don't have multiple stochastic layers, just a single stochastic layer. Then you have a recognition model, which is a deterministic recurrent network. Right? So in this case, when we look at VAEs, your recognition model was a feed-forward network. In this case, it's a recurrent network. Right? So obviously, you can extend these ideas to modeling, to taking time into account. Right? And attention, or the alignment, you're essentially focusing on different words at different type steps when generating patches and placing them on the canvas. So for example, when you're generating in a second time step, you can pay attention to the word person. Maybe you draw a person at that point. At the next time, when you're paying attention to the mountain, you might be drawing the mountain, right? So here's how the generative model works. You sample the latent state, Z, just like we've seen in VAEs, but conditional on the previous time steps. right, on the previous z's. So you can think of it as an autoregressive model in the latent space, which is given by a Gaussian distribution with some mean and some variance, depending on the previous time step. Then there is an alignment operation that looks at the language, finds out what words to pay attention to in order to generate what the alignment should be, and then based on this alignment, it generates the latent state. And then there is a writing operation, which takes the latent state, produces the right operation, which is then get applied into the actual likelihood, and actually you're filling in using Bernoulli's model, basically figuring out what this distribution should be. Right? This is what you're writing, and here you're just transforming it through the sigmoid function and defining the likelihood function. So let me show you quickly what the alignment operation does, which you can think of it as figuring out dynamically what the sentence representation at time t should be. In the next class, when we're going to look at reading comprehension tasks, we're going to be using a lot of this particular alignment operations that, again, allow you to dynamically choose which part of the sentence to pay attention to, right? And the alignment operation is very simple. It's a weighted average of bidirectional hidden states. So you're saying that your representation of sentence at time t is going to be given by the weighted average of these hidden state representations, right? So if I put all my weight on the person and not put any weight on the rest, then my representation at time t, st, is going to be heavily, paying attention towards the person representation and ignoring everything else, right? And so these alignment probabilities are basically computed by using softmax function, and the softmax function depends on the previous hidden state, and it depends on your current embedding of the overall HK lang is just overall representation of the entire sentence. So it looks at the previous state, it looks at the overall representation of the sentence, and then decides what it should be paying attention to. And this entire operation is, again, differentiable. You can backprop through it. And as we've seen before, what you can do here is you can maximize the variational low bound on the marginal log probability of the correct image given the caption. So this is sometimes is called conditional model or conditional VAE, because given the caption, it actually defines what my prior should be, and then I'm generating my data given the caption. So ultimately, I am trying to model log probability of x given y. X is my image, y is my sentence, right? And this is what the model looks like. And then there is additional post-processing step where I think that Elman, who was doing this work, used the adversarial network trained on residual of Laplacian pyramid to sharpen the generated image. So it was done, VAE generates the image, and then it goes through the GAN type of objective that basically sharpens the image a little bit. And if you look at the COCO data set, you have about 83,000 images. Each image contains about 5 captions, and that's a standard data set for evaluating caption generation systems. And this is what the model can do. So it says a yellow school bus parked in the parking lot, and then a red school bus parked in the parking lot, even though it never sees images of red school buses, right? It sort of identifies, the only difference between these two captions is one word, yellow versus red, right? So it learns some representation of the red and associates it with the color of the object. A green school bus parked in the parking lot, so it kind of, that's actually pretty, not so bad, right? You see some kind of object here, maybe a car, and it paints it green. So again, the only difference is, it's probably seen green buses, but it's never seen green school buses or blue school bus parked in the parking lot, right? So it sort of is able to generate these different colors. Here's another one, large commercial plane flying in clear skies versus rainy skies, right? One thing to note is that this X in pixel space and this X is in pixel space are very different, right? Even though the underlying representation might be the same because you have an airplane somewhere in the skies, the actual images are very different in the pixel space. If you look at the L2 distance in the pixel space, they're going to be very far away from each other. And the model is able to capture that, and the only difference is one says clear, the other one says rainy. So the difference to the input to the model is just these two words. Everything else is the same. So the fact that it's able to change the colors, the fact that it's able to understand what's clear versus rainy is interesting because it picks up on those representations, which is generally very difficult to pick, particularly if you want to generate the models. And obviously, this is the case where you're generating something that doesn't exist. Well, no. This is you generating something that doesn't exist, right? So here's the elephants walking across dry grass field versus green grass field. So it has some notion dry versus green. So that's interesting. And then the student was basically saying, well, how about generating something? Oh, this is another case. Chocolate dessert on the table, a bowl of bananas on the table. Yeah, it's okay, yeah. So here's where it fails. A vintage photo of a cat or vintage photo of a dog. So when you get to the fine grain, it's very difficult to generate cats versus dogs. So you basically see no difference between those images, at least at this stage. And again, these are all generated using VAE type of objective. And then you can say, just looking at the quality of comparison, group of people walk on the beach with surfboards. This is what you can do with VAEs. This is LabGAN. This is another model based on generative adversarial nets. These are conv, deconv VAE. These are fully connected VAE. So there are a bunch of different things you can do. Generally, it's very difficult to be able to generate images of novel scenes based on captions. You can also do, one of the things you can do is you can evaluate these models because they give you proper probability distributions, P of X. So you can evaluate the bounds. The numbers themselves don't really matter that much. What's interesting is to look at the gap between test and training. If the gap is not that large, that means that the model is not overfitting. If the gap is very large, that means that the model is overfitting. And overfitting is bad because it basically says that I'm just fitting the training data. I'm not able to generalize to the test examples. So for these kinds of models with VAEs and extensions of VAEs, we can actually properly estimate log probability of the data. You can also do novel scene compositions. Like here's an example, a toilet sits open in the bathroom. It was one of the captions. Well, I don't know if you can see toilet seats sometimes, right? Or you can generate the toilet sits open in the grass field, right? So Elman was doing these experiments to say how well can you go from here to here. That's not bad, right? And then the student who was doing this project basically noticed that you can actually do very well by asking Google. So if you take this query, a toilet seat sits open in the grass field, put it in the Google query for image retrieval, you get this, right? It's pretty good, right? This is really good. How can you beat that if I ask you to build a generative model, right? You can't really beat that. But the good news is that when we put the paper on archive, after 2 weeks, if you actually type in this query into Google search, this image comes up in the rankings as being ranked higher than this image. And the reason for this is because when you look at these images, more people would be clicking on this image to figure out what the heck is this. And so by clicking more on that image, Google ranking system basically says, well, that must be a better image than this. So we've convinced Google that this is a much better representation of the meaning of the sentence than this one, right? People don't click on boring stuff. People click on interesting stuff, right? So that's good, right? Okay, so in the last 10 minutes, what I'd like to do is I'd like to give you an intuition behind another class of models, which are called generative adversarial networks. So this class of models have become very popular because it also produces pretty good results. And I wanted to give you an intuition behind what these models are. So one of the interesting things about generative adversarial networks is there's no explicit assumption on the density for P of X, right? Only need to be able to sample from it, so you don't need to be able to evaluate it, right? It's both plus and minus. It's plus because you can do whatever you want to do because you don't really have to define proper density. It's minus because it's very difficult to evaluate these models, very difficult to properly evaluate these models. How well do they generalize? There is no variational learning, no maximum likelihood estimation, no Markov chain Monte Carlo. So how do you do that? And the idea is by playing a game. So you're setting up a game between two players. There is a discriminator and there is a generator. Discriminator is trying to discriminate between a sample from the data distribution and a sample from the generator, right? So essentially, the discriminator is trying to discriminate between true samples, true data, and fake samples, samples generated from the model, right? I don't know, remember when we looked at deep Bayes machines, I've shown you two panels, and I asked you to say which one is real, which one is fake, right? Essentially, the discriminator is trying to do exactly that, right? It's trying to be really good at saying which is fake and which is real. The generator G is essentially attempting to fool the discriminator by generating samples that are hard for D to distinguish from the real data. So the role of the generator is to generate samples such that the discriminator would be confused. Actually, the output of the discriminator would always be 0.5, right? Because it will say, I have no idea if it is real or is it not real, right? Obviously, if my generator is not very good, then it would be very easy for discriminator to say, this is fake, this is real. Because this looks like garbage, this looks like MNIST digits, so obviously I can discriminate. Okay? So how do we set this up? So let's look at the example. Suppose you have X coming from the real data. So for example, X is your real face of a real image, of a real person. You get the input, you pass it through the differentiable function D. It could be convolutional model, fully connected model, whatever, residual networks, whatever you want to use. And the discriminator is going to be trained to output 1 because it's a real sample. Okay? So given all your real data, the goal for the discriminator is to output 1, to say it's a real example. Now, imagine I have a generative model. I have some input noise Z. Could be Gaussian noise, much like in variational autoencoders. Could be uniform noise, whatever you want to do here. You take Z, you pass it through differentiable function G. So it has to be differentiable. You can't have additional stochastic layers here. It has to be deterministic differentiable function G, and then you're generating X, right? Which is a fake face, for example, right? Or initially, you can imagine it's going to be generating a bunch of random noise. Now you take this X, you pass it through the same differentiable function D, and the goal is to output 0, right? Does that make sense? So think of how you would train a system like this. The way you would train a system like this is to say, well, give me some real data, give me some fake data, just generate some fake data, and then update parameters of my classifier such that for this data I assign 0, for this data I assign 1. Okay? Does that make sense? That's simple. So you can train it and see how well can you discriminate. And you can optimize the parameters of discriminator to say, given samples from my model and real data, train D. Now, how do you update parameters of G? What would you do? What you want to do is you want to say, look, how do I change parameters of G such that if I take my noise and I produce this thing, X, which is fake, in such a way that when I pass it through my discriminator outputs 1. That's what I want to do, right? So I want to be able to change parameters of G in such a way that when I sample X and I pass it through the discriminator will be outputting 1. That's what I want, right? And then you retrain your discriminator to say, no, I want my discriminator to really say this is fake, this is real. And the generator is always say, given fixed parameters of D, given my discriminator, how do I change G so that whatever I sample here, my model, discriminative model, would always predict 1, right? Does that make sense? And then you're updating discriminator, say, no, discriminator, don't predict 1, predict 0. And then the generator said, change my parameters so that whatever I would output, the discriminator would say it's 1, it's real, right? So now we can set up this min-max objective, which is very intuitive. And there's a whole bunch of different extensions. This is the basic one. You can imagine, if you look at the literature, there's a bunch of different new ways, new objective functions, and so forth. But the idea is basically the same, right? You want the discriminator to say, I want to separate fake from real. And the generator says, I want to be able to generate something that's hard to discriminate. Hard to say something, from being real. So this is a basic version of min-max objective. So let's look at, given G, we want to maximize this objective with respect to D, discriminator. Okay? What is this first term doing? This first term is basically saying, if I get samples from my data, and my output of my D is 1, then log of 1 is going to be 0. That's the maximum value I can achieve. Anything below that, log of 0.9 is always going to be, it's negative. So, to maximize this value, I would like to output 1 here for the real data, right? That's the first objective. The second objective is basically saying discriminator, classify and generate the samples as being fake. So samples that are drawn from the noise and are being passed through G to get my fake samples, I want the output of D to be 0. Because if the output of D is 0, then log of 1 is 0. And so the maximum possible I could achieve of this objective function is 0. Everything else is going to be below 0, right? So given my generator, this is nothing more than predicting log of the sigmoid, log of 1 minus sigmoid. This is essentially cross entropy, right? Except for sort of differentiating real from fake, okay? So given the generator, given my generative model, fitting this is just using cross entropy objective function. So this discriminator pushes this up. Now the generator pushes on the value of this function down. So what is the generator is trying to do? The generator is trying to say, generate me samples, G here, such that D would classify them as real. Because if I take the sample and the output of D is going to be 1, right? The log of 0 is negative infinity. I mean, I'll never output 1. I'll put like 0.9, for example, right? So you're trying to push this function down. You're trying to generate samples from G such a way that it would output a number close to 1. That's the objective of the G. So when you take the gradients, you can take the gradients with respect to G such that this objective is as small as possible. So you take the gradients and move it in direction where it's as small as possible, right? Or move in direction where it's smaller, right? Because the minimum is always going to be achieved when the output of D here is close to 1. So whatever fake I generate, whatever fake data I generate, if my discriminator says, oh yeah, it's close to 1, which means that I think it's real, then the value of this objective function is going to be very small. And that's the role of the generator. And it turns out that the optimal strategies for discriminator is to look at the probability of the data, divide probability of the data plus probability of the model, which is essentially being confused, between the real data and the fake data. Does that make sense? And then there's a whole bunch of different variations. This problem has a lot of problems. Logs, something you get closer to 0, you get big numbers, underflow, overflow, and stuff like that. So a bunch of ways of fixing it. There's a whole bunch of different models with different objective functions, but essentially they all follow this particular pattern, right? Very simple and very intuitive. The interesting thing, the important thing about GANs is that you have to be able to differentiate this objective function with respect to the generative parameters, G, right? Which basically means that the composition that goes from Z all the way to D has to be differentiable. So given Z, which is some noise, you're generating the phase. There is no stochasticity there. From phase, you feed in the classifier, you're producing, is it real, is it fake, right? So there is no density around generated samples. These are all just point masses. Given Z, you just generate one thing. There is no uncertainty, which makes it very difficult to evaluate these models properly, how good they are. Are they overfitting? Are they underfitting? And so forth. Here's an example of deconvolution GAN, which is basically you get a code, which is 100-dimensional code, and then you generate through deconvolution a high-resolution image. And this is what you can do with bedroom scenes. And there's a bunch of improvements on this model. You can generate bedroom scenes, and this is actually pretty good, right, if you look at these samples. Here's some examples of CFAR dataset. This is training, and these are the samples. So if you look at the images like this, you see the image of a horse. These images look remarkably good, right? A big question is that, is this a new horse that the model makes up, or is it like a training horse that you just fudge around and you generate? Because if it's a training horse that you just fudge around and generate, then it's not as impressive if it's generating a completely new horse. And in machine learning in general, we want to be able to generate new stuff. Right? Generating, as I mentioned, you could have a perfect generative model where my generative model is pick up a training example and show it to you. Right? That would be an amazing generative model. I can put a picture in my paper saying these are samples generated by my model. All of you are going to be very impressed, right? If I just randomly pick a training sample and show it to you, right? But obviously that would be, you know, a meaningless result. So the big question still remains, and it's an open question, is how do you evaluate these models, right? Because evaluation is very important. What you want to do is you want to say, here's a new horse. Does the model assign high probability to this image? Does the model believe that this is a reasonable image, right? Or does it say, I think it's same probability as random noise, basically, right? So if the model says it's the same probability as just some random noise, then you have a really bad generative model. These are the examples on ImageNet. And again, if you look at some of those examples, they look spectacular, right? So some images and so forth. Here are some examples of some cherry-picked examples. These are some generated images. Just kind of funny looking. That actually gives me hope that these models are actually able to generalize, because they're able to generate something that's not part of the training set. It's not good, but you can see like a, you know, this is, I guess this is a dog with like 5 or 6 eyes or something like that. So it's generating something that's not quite what you see at the training time. But at the same time, again, there is a still big open question. How can you properly evaluate these models? Because people have shown that they give very good results in terms of being able to generate, but the question still remains, can they generalize? Can they not generalize? Or all they're doing is just basically taking training images and moving things around a little bit and then generating it. So the jury is still out for these models. For VAEs, for variational autoencoders, you can actually evaluate log probabilities. So you can say something about, how good these models are. GANs tend to give much sharper images, which is visually more plausible and better looking, but generally far more difficult to evaluate properly. Okay, so on that note, I think I'm done. So next class, we're going to look at the case study of looking at language. So we'll come back to language a little bit and look at examples of doing reading comprehension. Question answering, reading comprehension using attention-based mechanisms and using deep learning for solving these tasks.